Somewhere in our galaxy, right now, there is a star so powerful, so blindingly luminous, that its own light is tearing it apart. Not in some quiet, slow, dignified way. In violent, catastrophic eruptions that blast entire solar masses of material into space in a matter of years. These stars shine millions of times brighter than our sun. They are among the rarest and most unstable objects in the entire universe. And they exist in a regime so extreme that the very radiation pouring out of their cores pushes against gravity with almost equal force. They are balanced on a knife's edge. And when that balance tips, even slightly, the star doesn't just flicker, it detonates layers of itself into the void. These are luminous blue variables, and their story is terrifying. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Let's start with something fundamental. Something that seems simple at first, but is actually the key to understanding everything we're going to explore tonight. How does a star work? What keeps it alive? What prevents it from collapsing under its own weight, or from flying apart in every direction? Because once you truly understand this balance, once you see the tension that holds a star together, you'll understand why certain stars cross a threshold that makes them the most dangerous, most unstable, most violently self-destructive objects in the entire universe. Every star, including our sun, exists in a state of constant tension. There are two opposing forces locked in a struggle inside every star that has ever existed. On one side, there is gravity. Gravity pulls everything inward. Every particle of matter in the star is attracted to every other particle. The sheer mass of the star creates an enormous gravitational force that wants to crush everything toward the center. If gravity were the only force at work, the star would collapse in a matter of minutes. It wouldn't be a star at all. It would just be a ball of matter falling inward, getting denser and hotter, compressing toward a point. But something stops that collapse. On the other side of this struggle, there is pressure, outward pressure, pushing against gravity, holding the star up, preventing it from caving in on itself. And this is where things start to get interesting, because the source of that outward pressure depends entirely on what kind of star you're talking about. For a star like our sun, the dominant outward force is gas pressure. Deep in the sun's core, temperatures reach about 27 million degrees Fahrenheit. At these extreme temperatures, hydrogen nuclei overcome their natural electromagnetic repulsion and fuse together to form helium. This process is called nuclear fusion. In the process, a small amount of mass is converted directly into energy, following Einstein's famous equation relating energy to mass and the speed of light. That energy radiates outward from the core as photons, pushing against the surrounding material on their way out. The heat generated by fusion also keeps the gas in the core incredibly hot, and hot gas expands. It pushes outward in every direction. This thermal gas pressure is what primarily holds the sun up against the crushing force of gravity. The sun has been maintaining this balance for about 4.5 billion years, and it will continue doing so for roughly another 5 billion years. It's remarkably stable. The inward pull of gravity is almost perfectly matched by the outward push of gas pressure and the radiation created by fusion. If the star contracts slightly, the core gets hotter, fusion speeds up, and the extra pressure pushes the star back out. If it expands slightly, the core cools, fusion slows, and gravity pulls it back in. It's a self-correcting system, like a thermostat. The Sun is in equilibrium, a state astronomers call hydrostatic equilibrium, and it is remarkably difficult to disturb. Now, this might make you think that all stars work the same way, that every star is just a bigger or smaller version of the Sun, maintaining the same kind of balance, living a similar kind of life. But that is not true. And this is where the story takes a dramatic turn, because as stars get more massive, the physics changes. Not a little, fundamentally. In a star like the Sun, the primary fusion process is called the proton-proton chain. It's a relatively slow process. Individual protons collide and fuse step by step, building helium nuclei gradually. The energy output is modest by stellar standards. The Sun produces about 382 trillion joules of energy every single second. That sounds like an absurd amount of power, and it is by human standards. But by the standards of truly massive stars, the Sun is barely a candle. When you start looking at stars that are significantly more massive than the Sun, the fusion process itself changes. Stars more massive than about 1.5 times the Sun's mass primarily use a different fusion pathway called the CNO cycle. This process uses carbon, nitrogen, and oxygen as catalysts to fuse hydrogen into helium, and it is far more temperature sensitive than the proton-proton chain. A small increase in core temperature produces a much larger increase in energy output. This means that massive stars don't just produce a little more energy than the Sun, they produce enormously more energy. And this is where a critical shift happens. In stars like our Sun, gas pressure does most of the work holding the star up. Radiation pressure, the outward push of light itself, plays a relatively minor role. Photons do exert pressure when they interact with matter. Every photon that is absorbed or scattered by an atom gives that atom a tiny push. In the Sun, this push is real, but it's small compared to the thermal gas pressure. But in massive stars, things are different. As a star's mass increases, its core temperature rises dramatically. The fusion reactions become far more efficient, producing vastly more energy. And all that extra energy means vastly more photons pouring out of the core. More photons means more radiation pressure. And as you go to higher and higher masses, radiation pressure doesn't just increase. It begins to dominate. It starts to overtake gas pressure as the primary force holding the star up against gravity. This transition is not gradual, it's steep. By the time you reach stars of about 20 to 25 solar masses, radiation pressure has become a major contributor to the star's structural support. By the time you reach stars of 50 or 60 solar masses, radiation pressure is doing most of the heavy lifting. The star is being held up not primarily by the thermal motion of its gas, but by the sheer force of its own light, pushing outward against gravity. And this changes everything. Because radiation pressure behaves differently than gas pressure. Gas pressure is stable. It responds smoothly and predictably to changes in temperature and density. That's why the Sun's thermostat works so well. Radiation pressure is less forgiving. It can amplify small disturbances rather than dampening them. A star supported primarily by radiation pressure is fundamentally more fragile, more sensitive to perturbation, more prone to instability than a star supported by gas pressure. It's the difference between balancing on a flat floor and balancing on a knife's edge. Both are balance, but one is far more precarious than the other. Now let's talk about luminosity, because this is where the numbers become almost absurd. Luminosity is the total amount of energy a star radiates into space every second. It's the star's true brightness, not how bright it looks from Earth, but how much power it actually produces. And luminosity increases with mass far faster than you might expect. The relationship between a star's mass and its luminosity follows a steep power law. For main sequence stars, the ones that are still fusing hydrogen in their cores, luminosity scales roughly as mass raised to the power of about 3.5. This means that if you double a star's mass, you don't double its luminosity. You increase it by roughly 11 times. If you increase a star's mass by a factor of 10, you increase its luminosity by more than 3,000 times. Let me show you what this means with real numbers. The Sun has a luminosity of 1, by definition. Astronomers use the Sun as the baseline. A star with 10 times the Sun's mass doesn't shine 10 times brighter. It shines roughly 3,000 to 5,000 times brighter. A star with 25 times the Sun's mass shines roughly 80,000 to 100,000 times brighter. A star with 50 times the Sun's mass shines roughly 300,000 to 500,000 times brighter. And when you get to the true giants, stars with 100 or more times the mass of our Sun, the luminosity reaches into the millions. A star 100 times the mass of the Sun can be more than 3 million times more luminous. These numbers are not abstractions. They represent real physical power. A star that is 3 million times more luminous than the Sun is pouring 3 million times more energy into space every single second. That energy is carried by photons, and those photons exert pressure on everything they encounter. The more luminous the star, the harder its light pushes outward. And at these extreme luminosities, that outward push becomes almost uncontrollable. And there is another detail that makes this even more intense. The photons produced in a star's core do not simply fly straight outward and escape. They are trapped. Every photon produced by fusion in the core is almost immediately absorbed by the surrounding material, then re-emitted in a random direction, then absorbed again, re-emitted again, absorbed again. This process repeats millions upon millions of times. In a star like our Sun, a photon produced in the core takes an estimated 100,000 to 200,000 years to random walk its way to the surface and escape into space. The photon is bouncing around inside the star for longer than modern humans have existed as a species. In a massive star, the interior is even more opaque in certain regions. The photons are trapped more effectively, and the radiation pressure they exert during their long, tortuous journey outward is correspondingly more intense. Every interaction between a photon and an atom transfers momentum. Every absorption and re-emission is a tiny push. And when trillions upon trillions of photons are all trapped inside a star, all pushing outward simultaneously, the cumulative force is enormous. This scaling has another devastating consequence. Massive stars burn through their fuel at a rate that is wildly disproportionate to how much fuel they have. You might think that a star with 50 times the Sun's mass has 50 times as much hydrogen fuel, and therefore should live 50 times as long. But that's not how it works. A star with 50 times the Sun's mass does have roughly 50 times as much hydrogen. But it burns through that hydrogen not 50 times faster, but hundreds of thousands of times faster. The result is that massive stars live incredibly short lives compared to the Sun. The Sun will live for about 10 billion years on the main sequence, steadily fusing hydrogen in its core for an almost incomprehensible span of time. A star with 10 times the Sun's mass will exhaust its hydrogen in about 20 to 30 million years. That sounds like a long time, but it's less than 1% of the Sun's lifetime. A star with 50 times the Sun's mass burns through its fuel in roughly 3 to 5 million years. A star with 100 times the Sun's mass might last only 2 to 3 million years. To put this in perspective, if the Sun's lifetime were represented by a single calendar year, a star with 50 solar masses would burn out in about 4 hours. These massive stars live fast and die violently. They don't have time for a long, stable existence. They ignite, they blaze with incomprehensible power, and they are gone in what is, by cosmic standards, the blink of an eye. And during their brief lives, their extreme luminosity puts them in constant danger of a kind of self-destruction that no smaller star will ever experience. This brings us to what might be the most important concept in all of massive star physics: the Eddington limit. This idea was developed in the 1920s by the British astrophysicist Arthur Eddington, who was one of the first scientists to truly understand how stars work. Eddington realized something profound. There is a maximum luminosity that any star of a given mass can sustain, a ceiling above which the outward push of radiation overwhelms the inward pull of gravity. Here's how it works. Inside a star, photons are constantly being produced by fusion in the core. These photons travel outward, but they don't travel freely. They interact with the material in the star. They are absorbed, scattered, and re-emitted by atoms and electrons in the stellar interior. Every time a photon is absorbed or scattered by a particle, it transfers a tiny amount of momentum to that particle, giving it a small outward push. Now, if the star is not too luminous, these tiny pushes are negligible compared to the gravitational force pulling those same particles inward. Gravity wins easily. The star stays together. But as the luminosity increases, the number of photons increases. More photons means more pushes. More pushes means more outward force on the material. At some critical luminosity, the outward force from radiation exactly equals the inward force from gravity. This is the Eddington limit. At this point, the star is in a precarious state. Every particle in its outer layers is being pulled inward by gravity and pushed outward by radiation with exactly equal force. The material is effectively weightless. It's not bound to the star anymore in any meaningful sense. And if the luminosity exceeds the Eddington limit, even slightly, the outer layers of the star are no longer held down by gravity. They are pushed outward by radiation pressure. The star begins to lose mass. Material is driven off the surface and into space by the sheer force of the star's own light. The Eddington luminosity depends on the star's mass. A more massive star has stronger gravity, so it can tolerate a higher luminosity before reaching the limit. For a star with the mass of our Sun, the Eddington luminosity is about 32,000 times the Sun's actual luminosity. The Sun is nowhere near its Eddington limit. It's not even close. For a star with 50 solar masses, the Eddington luminosity is about 1.5 million times the Sun's luminosity. And for a star with 100 solar masses, it's about 3.2 million times the Sun's luminosity. Now here's the critical problem. Remember that luminosity scales with mass raised to roughly the power of 3.5, while the Eddington limit scales linearly with mass. As mass increases, the actual luminosity climbs far faster than the Eddington limit does. This means that as stars get more massive, they get closer and closer to their Eddington limit. Low-mass stars like the Sun are far below their limit, but the most massive stars are right at the edge. Stars above roughly 100 solar masses are producing luminosities that are dangerously close to or even exceeding their Eddington luminosity. They are shining so hard that their own light is threatening to blow them apart, and it gets worse. The Eddington limit, as I've described it so far, assumes a particular kind of interaction between photons and matter, specifically electron scattering, where photons bounce off free electrons. But there's another factor that makes things even more unstable: opacity. Opacity is a measure of how effectively material absorbs or scatters light. The higher the opacity, the more momentum photons transfer to the material, and the stronger the outward push of radiation becomes. In the outer layers of massive stars, the opacity is not constant. It changes with temperature and density, and there are certain temperatures at which opacity increases dramatically. One of the most important of these occurs around 150,000 to 200,000 degrees, in a region where iron and iron group elements become partially ionized. At these temperatures, iron atoms have electrons in configurations that are extremely efficient at absorbing photons. The opacity spikes. This is sometimes called the iron opacity bump, and it has enormous consequences for massive stars. When a star's outer layers happen to be at temperatures near this iron opacity bump, the effective Eddington limit drops. The material becomes more opaque, which means the radiation pushes harder against it. A star that was just barely below its Eddington limit can suddenly find itself above it, simply because the opacity in its outer layers increased. The outer layers start to be pushed outward. As they move outward, they cool. And as they cool, their opacity can change again, sometimes dropping, which reduces the radiation force and allows gravity to pull the material back. This creates a deeply unstable situation. The star's outer layers can oscillate, pulsing in and out, driven by the interplay between opacity, temperature, radiation pressure, and gravity. In mild cases, this produces variability, changes in the star's brightness over months or years. In severe cases, it produces catastrophic eruptions where enormous amounts of material are violently ejected from the star in a single event. This is the regime where the most massive, most luminous stars live. Not a stable equilibrium like the Sun enjoys, but a constant, precarious, knife-edge balance where even small perturbations can trigger enormous instability. This is the physics that creates the most violent, most unpredictable, most self-destructive stars in the universe. Let me give you a sense of how close to the edge some real stars are. The most massive stars astronomers have observed are staggering objects. R136, A1, located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, is one of the most massive and luminous stars ever discovered. It has an estimated mass of roughly 150 to 200 times the mass of our Sun. Its luminosity is approximately 6 million times the Sun's luminosity. This star is radiating so much energy that it loses mass continuously, shedding material from its surface in a powerful stellar wind that blows at speeds exceeding thousands of kilometers per second. It is very close to its Eddington limit, and despite being one of the most massive stars known, it is losing mass so rapidly that it may have already lost tens of solar masses over its short lifetime. The Pistol star, located near the center of our own Milky Way galaxy, is another example. It has an estimated luminosity of roughly 1.6 million times the Sun's luminosity, and a mass of perhaps 25 to 30 solar masses today, though it was almost certainly far more massive when it was born, likely exceeding 100 solar masses at birth. The Pistol star is surrounded by the Pistol Nebula, an enormous cloud of gas that was ejected by the star in violent eruptions roughly 4,000 to 6,000 years ago. This nebula contains roughly 10 solar masses of material, 10 times the mass of our entire Sun, blasted off the surface of one star by the force of its own radiation. This is not abstract physics. These are real objects that exist right now in our galaxy and in neighboring galaxies. They are stars that are so luminous, so close to the breaking point that they are actively tearing themselves apart. And this is what makes the most massive stars fundamentally different from stars like the Sun. The Sun is stable. It sits comfortably below its Eddington limit, held in perfect balance by a reliable thermostat mechanism. It will live for billions of years without drama. But the most massive stars occupy a regime where that thermostat breaks down, where the balance between gravity and radiation is so precarious that the slightest disturbance can trigger violent instability, where the star's own light becomes its greatest enemy. These stars are not slowly burning through their fuel in quiet dignity. They are fighting a losing war against their own luminosity, shed en masse in winds and eruptions, growing lighter and less gravitationally bound with each passing century. They are, in the most literal physical sense, stars that are too bright to hold themselves together. And here is something that makes all of this even more remarkable. Stars this massive are extraordinarily rare. Nature overwhelmingly favors small stars. When new stars form from collapsing clouds of gas and dust, the distribution of masses follows a pattern that astronomers call the initial mass function. This pattern is steep. For every star born with 10 times the mass of our Sun, there are roughly 1,000 stars born with the mass of our Sun or less. For every star born with 50 solar masses, there are tens of thousands of Sun-like stars. And for every star born with 100 solar masses or more, there are hundreds of thousands or even millions of ordinary low-mass stars. The extreme end of the stellar mass spectrum is almost empty. The universe makes very, very few of these giants. Red dwarfs, small cool stars with less than half the mass of our Sun, make up roughly 70% of all stars in the Milky Way. Stars as massive as 10 solar masses are already uncommon. Stars above 50 solar masses are genuinely scarce, and stars above 100 solar masses, the ones that will eventually become the most violently unstable objects in the universe, are so rare that you could search an entire galaxy and find only a handful. This rarity makes them precious scientifically. Every one of them is a laboratory for physics that cannot be studied anywhere else. This is the foundation of everything we're going to explore tonight. The physics of extreme mass, extreme luminosity, and the Eddington limit. Because there is a specific type of star that lives right at this breaking point. A star so massive and so luminous that it exists in a state of near permanent instability, oscillating between states, erupting violently, shedding its own outer layers in events so powerful they can briefly outshine entire galaxies. These stars are the rarest, most extreme, most violently unstable stellar objects we have ever discovered. And they are called luminous blue variables. To understand what they are, what makes them different from every other type of massive star, and why they can literally tear themselves apart, you first needed to understand the physics we've just laid out. The balance of forces inside a star, the steep relationship between mass and luminosity, the Eddington limit, the iron opacity bump, the fragility of radiation-supported envelopes. All of these ingredients come together in luminous blue variables to create something extraordinary and terrifying. A star at war with itself. A star so powerful that its own energy is the thing that destroys it. And the question of exactly how this tearing happens, what triggers the eruptions, what determines how much mass is lost and how fast, that is what we need to understand now. Now that we understand the physics, the balance of forces inside a star, the steep relationship between mass and luminosity, the Eddington limit, and the fragility that comes with being held up by your own light, we can ask the central question of this entire exploration. What exactly is a luminous blue variable? Because the name itself sounds almost contradictory. Luminous, blue, variable. Each of those words carries specific meaning in astronomy, and when you put them together, they describe something that should barely be possible. A star so luminous it rivals small galaxies, so hot it glows blue-white, and so unstable that its brightness, its temperature, and even its physical size change dramatically over timescales that are, by stellar standards, absurdly short. These are not theoretical objects. They are real. They exist in our galaxy right now. And understanding what they are, what makes them different from every other kind of massive star, and why they occupy a category all their own is essential to understanding the most extreme limits of stellar existence. Let's start with the basics. A luminous blue variable is an evolved, extremely massive star. When astronomers say evolved, they mean it has already spent a significant portion of its life. It has left the main sequence, which is the long, stable phase where a star fuses hydrogen in its core. Main sequence stars are in equilibrium. They've found their balance, but an LBV has moved past that stage. It has burned through a substantial fraction of its hydrogen fuel, and its internal structure has changed as a result. It is no longer the star it was when it was born. These stars typically began their lives with masses of at least 40 to 50 times the mass of our Sun, and some were born exceeding 100 solar masses. During their main sequence lives, they were already extraordinary, already blindingly luminous, already burning through fuel at staggering rates, but they were relatively stable. The thermostat mechanism we discussed earlier, the self-correcting balance between gravity, fusion, and pressure, was still functioning. They were hot, blue, and powerful, but they were holding together. An LBV is what happens when that stability ends. As these massive stars evolve, as they burn through their hydrogen and begin fusing heavier elements in their cores, their internal structure shifts. The core contracts and heats up. The outer layers respond by expanding. The star grows larger, and crucially, its luminosity changes, not by a small amount. The luminosity of these evolved massive stars is so extreme that they push right up against the Eddington limit we discussed earlier. They enter a regime where radiation pressure is no longer just one component of the star's support structure. It is the dominant force, and that changes everything about how the star behaves. An LBV typically has a luminosity somewhere between roughly several 100,000 and 5 million times the luminosity of our Sun. Let those numbers sit in your mind for a moment. Hundreds of thousands to millions of suns. A single star producing as much light as millions of ordinary stars combined. At these luminosities, The outward push of radiation on the star's outer layers is immense. The material in the outer envelope is barely gravitationally bound. It is sitting on the edge of being blown away entirely by the star's own light. And this is what defines an LBV more than anything else. It is a star that lives at the boundary between holding itself together and tearing itself apart. To understand where LBVs sit in the grand scheme of stellar evolution, astronomers use a tool called the Hertzsprung-Russell diagram, often shortened to the HR diagram. This is a plot that maps stars according to two properties: their luminosity, which goes on the vertical axis, and their surface temperature, which goes on the horizontal axis. The horizontal axis is arranged in a way that might seem counterintuitive. Temperature increases to the left, not to the right. So hot blue stars appear on the left side of the diagram, and cool red stars appear on the right. The HR diagram is one of the most powerful tools in stellar astrophysics, because a star's position on this diagram tells you an enormous amount about what kind of star it is, what stage of life it's in, and what its future holds. Most stars spend the majority of their lives on the main sequence, a diagonal band running from the lower right, where cool dim red dwarfs live, to the upper left, where hot luminous blue giants reside. Our sun sits comfortably in the middle of the main sequence. It's been there for 4.5 billion years, and will stay there for roughly another 5 billion. Massive stars begin their lives on the upper left of the main sequence. They are hot, blue, and extremely luminous. But they don't stay there for long. Their enormous luminosities mean they burn through fuel quickly, and as they evolve, they move across the HR diagram, changing temperature and luminosity as their internal structure shifts. Now, here is where things get fascinating and where LBVs enter the picture. When astronomers plot the positions of known stars on the HR diagram, they notice something remarkable at the highest luminosities. There is an upper boundary, a ceiling in the diagram above which almost no stable stars exist. This boundary was identified in the 1970s and early 1980s by astronomers Roberta Humphreys and Chris Davidson, and it is now called the Humphreys-Davidson limit. The Humphreys-Davidson limit is not a straight horizontal line. It slopes across the upper region of the HR diagram. At the hottest temperatures, on the left side, stars can reach very high luminosities and remain relatively stable. But as you move toward cooler temperatures, toward the right side of the diagram, the maximum observed luminosity drops. At surface temperatures around 7,000 to 8,000 degrees, the upper luminosity limit is significantly lower than at the hottest temperatures. The region above this boundary is sometimes called the forbidden zone, though not because stars are literally forbidden from entering it. They can enter it, but they cannot stay there. Any star that finds itself above the Humphreys-Davidson limit becomes violently unstable. Its outer layers are so loosely bound, so dominated by radiation pressure, that the star cannot maintain a stable configuration. It erupts, it sheds mass, it oscillates. It does whatever it takes to get back below the limit, even if that means throwing away enormous quantities of its own material. LBVs live right at this boundary. They cluster along the Humphreys-Davidson limit on the HR diagram, sitting at or just below the maximum luminosity the universe will allow for stars at their temperature. They are pressed right up against the ceiling, and periodically, through eruptions and instabilities, they punch through it, temporarily exceeding the maximum stable luminosity before falling back down. This is what makes their position on the HR diagram so distinctive and so dangerous. They are not sitting in a comfortable, stable region. They are perched on the edge of a cliff, and they keep falling off. Now, you might be wondering how LBVs are different from other types of massive stars. There are several categories that can seem confusingly similar if you don't know what distinguishes them. So let's be precise. Blue supergiants are hot, massive, luminous stars. They have surface temperatures typically ranging from about 10,000 to 50,000 degrees, and luminosities that can reach hundreds of thousands of times that of the Sun. Some blue supergiants are very massive, with masses of 20 or 30 or even 40 solar masses. They sit on the left side of the HR diagram, hot and bright. But most blue supergiants are not LBVs. The critical difference is stability. An ordinary blue supergiant, while certainly more volatile than a star like our Sun, is still in a relatively stable phase of evolution. It has found a configuration where its luminosity and temperature can be sustained for an extended period. It is not undergoing dramatic, unpredictable changes in brightness or violent eruptions. It is a massive star living out one of the stable chapters of its life. An LBV, by contrast, is a blue supergiant that has crossed into instability. It has reached or exceeded the luminosity threshold where stable existence is no longer possible. Its position on the HR diagram is not fixed. It moves. Its temperature changes. Its brightness fluctuates. It is a blue supergiant that has entered a crisis. Red supergiants are another common category of massive evolved star. These are the cool giants. A Betelgeuse in the constellation Orion is perhaps the most famous example. Red supergiants have surface temperatures of only about 3,000 to 4,000 degrees. They're cool by stellar standards, but they are enormously large. Betelgeuse has a diameter that, if placed where our Sun is, would extend past the orbit of Mars. Red supergiants have high luminosities, typically tens of thousands to hundreds of thousands of times that of the Sun. But they are fundamentally different from LBVs in almost every way. They are cool, not hot. They are extended, not compact. And while they do experience some instability and mass loss, it is generally milder and more gradual than what LBVs undergo. Red supergiants lose mass through relatively slow stellar winds, not through the catastrophic eruptions that characterize LBVs. The evolutionary relationship between LBVs and red supergiants is complex and still debated among astronomers. Some theories suggest that the most massive stars may oscillate between blue and red supergiant phases, passing through LBV instability on the way. Others suggest that the most massive stars never become red supergiants at all. They may be so luminous that they lose too much mass during the LBV phase to ever cool down to red supergiant temperatures. Their envelopes are stripped away before they can expand that far. This remains an active area of research. Wolf-Rayet stars are perhaps the category most easily confused with LBVs because they are also extremely hot, extremely luminous, and associated with powerful stellar winds and mass loss. But there is a fundamental difference. A Wolf-Rayet star is a massive star that has already been stripped of its outer hydrogen envelope. Its surface is no longer hydrogen-rich. Instead, what you see when you look at a Wolf-Rayet star is the exposed helium core, or in some cases even deeper layers rich in carbon, nitrogen, or oxygen. These stars are extremely hot, with surface temperatures often exceeding 50,000 degrees. They are compact, dense, and intensely luminous. They drive powerful stellar winds that carry mass away at speeds of 1,000 to 3,000 kilometers per second. But the key distinction is this. A Wolf-Rayet star has already lost its hydrogen. An LBV still has hydrogen in its outer layers. The LBV is in the process of losing that hydrogen through winds and eruptions, and is thought to be in a transitional phase that will eventually lead to the Wolf-Rayet stage. The LBV is, in a sense, the precursor. The Wolf-Rayet star is what comes after, once the outer layers have been removed. If you think of a massive star's life as a story, the LBV phase is the crisis, the climax, the point where everything becomes unstable and the star begins violently shedding itself. The Wolf-Rayet phase is the aftermath, after the outer layers are gone and the exposed core burns furiously through its remaining fuel before the final collapse. This transitional nature is one of the most important things to understand about LBVs. They are not a permanent type of star. They are a phase, a stage that certain massive stars pass through during their evolution. And it is a relatively brief stage, lasting perhaps only a few tens of thousands of years, maybe 100,000 years at most. In a universe where stars can live for billions of years, and even massive stars live for millions of years, the LBV phase is extraordinarily short. It is a brief, violent interlude in the life of a star that is already living on borrowed time. This brevity is one reason LBVs are so rare. At any given moment, only a tiny fraction of massive stars are in this phase. Astronomers have identified only about a dozen confirmed LBVs in our entire galaxy, the Milky Way, with perhaps another dozen candidates. Neighboring galaxies like the Large Magellanic Cloud and the Andromeda Galaxy contain similar small numbers. Across all galaxies close enough for us to study individual stars, the total count reaches only about 40 to 50. Out of the hundreds of billions of stars in each of these galaxies, only a few dozen are LBVs. They are among the rarest objects in the stellar zoo, and every one of them is extraordinary. But astronomers did not always know that these stars formed a coherent class. For centuries, the stars we now call luminous blue variables were studied as isolated curiosities, individual oddities that didn't seem to fit neatly into any existing category. And the story of how they were finally recognized as a distinct type of object is itself a fascinating piece of scientific detective work. P Cygni was perhaps the first LBV to attract serious attention, though no one knew what it was at the time. When it suddenly appeared as a bright, naked-eye star in the year 1600, astronomers recorded it as a nova, a new star. It faded, brightened again, faded again over the following decades, and eventually settled to a relatively constant brightness. For centuries, it remained a puzzle, a star that had appeared out of nowhere and then behaved in ways that no one could explain. Eta Carinae attracted attention much later, during its great eruption in the 1840s. Observers noted that a previously unremarkable star in the southern sky had suddenly become one of the brightest objects in the heavens. After the eruption faded, Eta Carinae dimmed dramatically, hidden behind the expanding dust cloud of its own making. For over a century, it was treated as a singular event, a strange outburst from a peculiar star not connected to P Cygni or to any broader pattern. Other variable, massive stars were catalogued over the decades. S Doradus in the Large Magellanic Cloud was noted for its irregular brightness changes. A.G. Carinae showed similar behavior. Hubble and Sandage identified luminous blue stars in other galaxies that seemed to exhibit analogous variability. but each of these was treated as an individual case. No one had yet recognized the underlying pattern connecting them. That changed in the 1980s, largely through the work of astronomer Peter Conti. It was Conti who proposed the term luminous blue variable in 1984, arguing that stars like Eta Carinae, P Cygni, S Doradus, and AG Carinae were not isolated curiosities, but members of a single physical class. They shared common properties: extreme luminosity, high mass, irregular variability, evidence of massive eruptions and powerful stellar winds. And crucially, they all occupied the same unstable region of the Hertzsprung-Russell diagram, clustered near the Humphreys-Davidson limit. Conti's insight was transformative. By recognizing these stars as a class, astronomers could study them collectively rather than individually. Patterns that were invisible when each star was treated as a one-off became clear when they were compared. The S Doradus type oscillations, the giant eruptions, the circumstellar nebulae, these spectral signatures of powerful outflows, all of these turned out to be shared features. Not quirks of individual stars, but defining characteristics of a physical category. The luminous blue variable class was born, and with it came the understanding that these stars occupied a specific, critical, and extraordinarily dangerous phase of massive stellar evolution. A phase where the most extreme physics in the stellar universe plays out in real time. Let me tell you about some of the most famous ones, because putting real names and real observations to this category helps you understand what these stars actually look like and how they behave. Eta Carinae is almost certainly the most famous LBV in existence. It is located in the Carinae Nebula, about 7,500 light-years from Earth. It is actually a binary star system. The primary star, Eta Carinae A, has an estimated current mass of roughly 100 to 120 solar masses and a luminosity of about 5 million times that of the Sun. This single star produces as much light as 5 million suns combined. It is one of the most luminous stars known in our galaxy. Eta Carinae is the poster child for LBV behavior. In the 1840s, it underwent what astronomers now call the Great Eruption, an event so violent and so luminous that it briefly became the second brightest star in the entire night sky, despite being nearly 8,000 light-years away. We will discuss this eruption in much greater detail later, because it is one of the most extraordinary events in recorded astronomical history. But for now, the important point is that Eta Carinae is a living example of an LBV. It is massive, luminous, unstable, and actively tearing itself apart. P Cygni is another famous LBV, located about 5,000 to 6,000 light-years from Earth. In the year 1600, P Cygni suddenly appeared in the sky as a new bright star, visible to the naked eye. At the time, people had no idea what it was. It had not been visible before, and its sudden appearance was a mystery. Over the following decades, it faded, brightened again, faded again, and eventually settled into a relatively stable brightness that it has maintained for about the last 3 centuries. What happened was an LBV eruption. P Cygni experienced a major outburst that dramatically increased its apparent brightness. The star then gradually settled back down, though it remains luminous and unstable. P Cygni is so important to our understanding of LBVs that a particular type of spectral line profile, a specific signature in the light from stars with strong outflowing winds, is named after it. When astronomers see a P Cygni profile in a star's spectrum, They know the star is losing mass through a powerful wind-blowing material outward from its surface. AG Carinae is another well-studied LBV in our galaxy. It has a luminosity of roughly 1 million times that of the Sun, and a mass estimated at around 50 to 70 solar masses. AG Carinae is surrounded by a ring-shaped nebula of ejected material, about 5 light-years across, that was blown off the star in past eruptions roughly 10,000 years ago. This nebula is direct physical evidence of the star's violent past. The material you see in that ring used to be part of the star. It was once inside AG Carinae, part of its outer layers, and was ripped away by the force of the star's own radiation and ejected into space. AG Carinae continues to show variability today, changing in brightness and temperature on timescales of years to decades. It is still an active LBV, still perched on the edge of instability. Estoradus is the LBV that gave its name to an entire class of stellar variability. Located in the Large Magellanic Cloud, about 160,000 light-years from Earth, Estoradus has a luminosity of roughly 1 million times the Sun, and has been observed to change significantly in brightness over periods of years to decades. These relatively modest variations, where the star brightens and fades without undergoing a catastrophic eruption, are called S Doradus variations or S Doradus cycles. They are characteristic of LBVs in their quieter phases, and they represent the star oscillating back and forth near its instability limit, changing temperature and apparent brightness as its outer layers adjust to the precarious balance between radiation and gravity. These examples illustrate one of the defining characteristics of LBVs, their variability. LBVs change. They are not static. Their brightness, their temperature, and their apparent size fluctuate on timescales ranging from months to decades to centuries. And this variability comes in different flavors, different intensities. Some of the variability is relatively mild. These are the S Doradus type variations I just mentioned. During these episodes, the star appears to shift between hotter and cooler states. When it is in a hotter state, its surface temperature might be around 15,000 to 25,000 degrees. It appears smaller and bluer. When it shifts to a cooler state, its surface temperature drops to perhaps 8,000 to 9,000 degrees. It appears larger and redder. Crucially, its total luminosity, the total energy it emits, stays roughly the same during these transitions. What changes is how that energy is distributed. In the hot state, the star emits more of its energy as ultraviolet light, which we can't see. In the cool state, it emits more invisible wavelengths, so it appears brighter to our eyes even though its total energy output hasn't changed much. This shift happens because the star's outer layers are expanding and contracting. When the outer envelope expands, the surface area increases but the surface temperature drops. The star looks bigger and cooler. When the envelope contracts, the surface area decreases and the temperature rises. The star looks smaller and hotter. These oscillations can take years or decades to play out, and they are the LBV's way of trying to find a stable configuration. But it never truly finds one. The star keeps oscillating, keeps shifting, because no stable state exists for it at its luminosity. But these mild variations are only part of the story, because sometimes LBVs don't just oscillate gently. Sometimes they explode, not in the final terminal sense of a supernova, where the entire star is destroyed, but in catastrophic eruptions, where the star ejects enormous quantities of mass in a very short time. These are called giant eruptions, and they are among the most violent non-terminal stellar events known to science. During a giant eruption, an LBV can increase in brightness by several magnitudes, becoming millions of times more luminous than the Sun. The star can eject anywhere from a fraction of a solar mass to 10 or even 20 solar masses of material in a single event lasting years or decades. The ejected material expands outward at speeds of hundreds of kilometers per second, forming an expanding nebula around the star. These eruptions are so luminous that they can be seen in other galaxies, mistaken at first for supernovae because of how bright they are. In fact, astronomers have identified a class of events called supernova imposters. These are eruptions of LBVs in distant galaxies that were initially classified as supernovae because of their brightness, only to be revealed later as non-terminal eruptions when the star was found to still be there afterward. The star didn't die. It just shed a massive chunk of itself in a burst so powerful it mimicked the death of a star. This is what makes LBVs unlike anything else in the universe. They are not steady, stable objects like most stars. They are not quietly aging like our Sun. They are not even steadily losing mass like the powerful but relatively predictable winds of Wolf-Rayet stars. They are erratic, unpredictable, explosive. They oscillate between states, sometimes gently, sometimes violently, and they are always, at every moment, on the verge of something dramatic. Their luminosity keeps them perpetually at the edge of what is physically sustainable. Their mass keeps them gravitationally bound, but only barely. And the interplay between these forces creates a star that is fundamentally different from anything else in astrophysics. Think of it this way. An ordinary star is like a ball resting in a valley. Push it slightly, and it rolls back to the center. It's stable. A blue supergiant is like a ball resting on a hill. It's balanced, but a strong push could send it rolling. An LBV is like a ball balanced on the point of a needle. The slightest breeze, the smallest vibration, can send it careening in any direction. And unlike a ball that falls and stops, an LBV doesn't settle. It bounces, oscillates, erupts, and reshapes itself continuously. It never finds rest because there is no rest to be found at its luminosity. The physics won't allow it. This brings us to perhaps the most important thing to understand about LBVs. They are temporary. The LBV phase is not where these stars live, it is where they are dying. Not in the final, explosive sense of a supernova, but in the slower, messier sense of a star that is progressively dismantling itself. Every eruption, every wind, every oscillation strips away mass. And as the star loses mass, its gravitational hold on its remaining material weakens. It becomes easier for the next eruption to strip away more. The star is caught in a cycle where instability drives mass loss, and mass loss drives further instability. It is a downward spiral, or more accurately, an outward spiral, as the star sheds layer after layer of itself into the surrounding space. The material that is ejected doesn't disappear. It forms nebulae, shells, and rings of gas and dust around the star. These structures are the physical evidence of past eruptions, the scars of a star's violent self-destruction. Every LBV that has been studied closely is surrounded by such structures. Eta Carinae has its homunculus nebula. AG Carinae has its ring nebula. P Cygni has its expanding shells. These nebulae are like crime scenes. They tell the story of what happened, how much mass was lost, how fast it was ejected, how long ago the eruption occurred. By studying these nebulae, astronomers can reconstruct the history of the star's violent outbursts. And all of this, the variability, the eruptions, the mass loss, the nebulae, all of it is driven by one fundamental fact. These stars are too luminous to hold themselves together. Their own light is destroying them. The radiation pouring out of their cores pushes against their outer layers with a force that nearly matches gravity. And in moments of crisis, when opacity increases or internal instabilities trigger perturbations, that radiation force exceeds gravity. The outer layers are launched into space. The star gets briefly lighter, which should make it more stable, but the core is still producing the same enormous luminosity. The remaining outer layers are now even more radiation dominated than before. The cycle continues. This is what a luminous blue variable is. Not just a big star, not just a bright star, not just a hot star. It's a star at the absolute extreme of what the universe allows. A star so massive and so luminous that the fundamental physics of radiation and gravity cannot sustain it in a stable state. A star that is, slowly and violently, tearing itself apart through the sheer force of its own brilliance. And the question of exactly how this tearing happens, what triggers the eruptions, what determines how much mass is lost and how fast, is where we go next. We now know what a luminous blue variable is. We know that it is an extraordinarily massive, extraordinarily luminous star perched at the very edge of physical stability. We know that radiation pressure, the outward push of the star's own light, nearly matches the inward pull of gravity. We know that these stars occupy a precarious region on the Hertzsprung-Russell diagram, clustered along the Humphreys-Davidson limit, the ceiling above which no star can exist in a stable state. But knowing that these stars are unstable is not the same as understanding why they erupt. And the why is where the real physics lives. Because the eruptions of luminous blue variables are not random. They are not cosmic accidents. They are the inevitable result of specific physical mechanisms operating inside the star, mechanisms that conspire to turn a star's own energy into a weapon against itself. Understanding these mechanisms is understanding why the most luminous stars in the universe can tear themselves apart. Let's begin with the most fundamental mechanism, the one that underlies everything else, the Eddington limit. We discussed this concept earlier, but now we need to go deeper into what happens when a star actually approaches it. Not as an abstract threshold, but as a lived physical reality inside the star's outer layers. When a star is well below its Eddington limit, the outward push of radiation on the stellar material is modest compared to gravity. Photons interact with the gas, pushing it outward slightly, but gravity easily wins. The material stays put, the star is stable. As the star's luminosity increases, or as conditions in the outer layers change to make the material more opaque, the radiation force grows relative to gravity. When the radiation force reaches about 70 or 80% of the gravitational force, something subtle begins to happen. The outer layers of the star become loosely bound. They are still gravitationally attached to the star, but only barely. The effective gravity that these layers feel, the net downward force after you subtract the outward radiation push, becomes very small. Imagine holding a heavy ball in your hand. If you're strong and the ball is light, you hold it easily. It would take a significant force to knock it out of your grip. But now imagine holding a ball that weighs almost as much as you can support. You can still hold it technically, but your grip is weak. The slightest bump, the smallest perturbation, could cause you to drop it. That is the situation in the outer layers of a star near the Eddington limit. The material is held in place, but weakly. Any disturbance, any change in conditions could tip the balance, and disturbances are not hard to find. Stars are not perfectly uniform, perfectly static objects. They are dynamic, turbulent, and filled with processes that create perturbations. Convection currents carry hot gas upward and cool gas downward. Pulsations send waves through the stellar interior. Nuclear burning in the core fluctuates. Magnetic fields shift and reconnect. Any of these processes can create a localized increase in energy flux, a brief surge of extra radiation pushing outward in one region of the star. In a stable star like the Sun, these perturbations are easily absorbed. The star adjusts and returns to equilibrium. But in a star near the Eddington limit, the margins are too thin. A perturbation that would be harmless in an ordinary star can push the local radiation force above the local gravitational force. And when that happens, the material in that region begins to accelerate outward. It starts to move away from the star. But this is where things get truly dangerous. Because the process is not self-correcting, it is self-amplifying. When material begins to move outward, away from the star, it cools slightly as it expands. And in certain temperature ranges, this cooling causes the opacity of the material to increase. Remember the iron opacity bump we discussed earlier? At temperatures around 150,000 to 200,000 degrees, iron and iron group elements become partially ionized in configurations that are extraordinarily efficient at absorbing photons. As the material cools into this temperature range, it becomes more opaque. More opaque material absorbs more photons. More absorbed photons means more momentum transferred to the material. More momentum means a stronger outward push. The material accelerates faster. As it accelerates and expands further, more material enters the critical temperature range. Opacity increases further. The radiation force grows stronger. The process feeds on itself. This is called a strange mode instability by some theorists, and it is one of the leading explanations for the oscillations and eruptions seen in LBVs. The iron opacity bump creates a positive feedback loop. A small initial disturbance is amplified by the opacity response of the material, driving larger and larger oscillations. In mild cases, this produces the S. doradus type variations we explored. The star's outer layers expand and contract rhythmically, driven by the interplay between opacity, radiation pressure, and gravity. Let's look at this more carefully because the physics of these oscillations reveals how finely balanced an LBV really is. During an S. doradus cycle, the star alternates between two apparent states. In one state, the star appears hot and compact, with a surface temperature of perhaps 15,000 to 25,000 degrees. In this state, the iron opacity bump is located deep inside the star, below the visible surface. The outer layers above it are relatively transparent, and radiation escapes fairly easily. The star looks blue, and its visual brightness is relatively low, even though its total luminosity, including ultraviolet emission, is enormous. Then, something triggers an expansion of the outer layers. Perhaps a surge in energy from below, perhaps a pulsation, perhaps a convective plume reaching the surface. Whatever the cause, the outer layers begin to move outward. As they expand, they cool. And as they cool, the iron opacity bump migrates outward, moving closer to the surface. Now the opaque region is higher up in the star's envelope. More of the star's radiation is being intercepted by opaque material near the surface. This has two effects. First, it traps energy, causing the outer layers to heat up slightly and expand further. Second, it redistributes the star's radiation from ultraviolet wavelengths, which our eyes cannot see, to visible wavelengths, which we can. The star appears to brighten dramatically, not because it is producing more total energy, but because more of that energy is coming out as visible light rather than ultraviolet. The star now looks cooler, bigger, and visually brighter. It has shifted from a hot blue state to a cooler, more visually luminous state. This is the expanded phase of the S Doradus cycle. Eventually, the expansion stalls. The outer layers become so extended that their density drops, and the opacity begins to decrease. With less opacity, radiation escapes more easily. The trapped energy leaks out. The radiation force on the outer layers weakens. Gravity reasserts itself, and the material begins to fall back inward. As it contracts and heats up, the iron opacity bump retreats deeper into the star. The outer layers become more transparent again. The star returns to its hot, compact state, and the cycle can begin again. This oscillation can repeat over timescales of years to decades. The star never settles into either state permanently. It slides back and forth, driven by the same opacity mechanism each time. And importantly, each cycle can be slightly different. The amplitude of the oscillation can vary. Sometimes the expansion is modest, sometimes it is more extreme. The star's behavior is not perfectly periodic or perfectly predictable. It is quasi-periodic, irregular, and sometimes chaotic. This is the hallmark of a system near a critical threshold. A system where small differences in initial conditions can lead to very different outcomes. But S Doradus cycles are the mild version of LBV instability. They involve changes in the star's apparent brightness by perhaps 1 to 2 magnitudes over years or decades. Impressive, but not catastrophic. The star remains intact. It loses mass through an enhanced stellar wind during these episodes, but the mass loss is relatively modest, perhaps a few 10,000ths of a solar mass per year. The star is shedding, but slowly. Giant eruptions are something else entirely. These are events where the instability mechanisms that drive S Doradus variations are amplified to an extreme degree, producing catastrophic mass loss on a scale that dwarfs anything seen in the milder oscillations. And the best way to understand what happens during a giant eruption is to look at the most famous one in recorded history, the Great Eruption of Eta Carinae. Eta Carinae, the star we encountered earlier, holds a critical detail we have not yet discussed. It is not a single star. It is a binary system. Its companion, Eta Carinae b, is itself a formidable object, estimated at perhaps 30 to 80 solar masses. The two stars orbit each other in a highly elliptical path, with a period of about 5.5 years. This means that a star already producing roughly 5 million solar luminosities, already pressed hard against its Eddington limit, is also being gravitationally perturbed by a massive companion sweeping close to it every few years. That gravitational perturbation may be one of the keys to understanding what happened next. In the 1840s, something extraordinary happened. Eta Carinae underwent a catastrophic eruption that lasted roughly 2 decades, from the late 1830s through the late 1850s, with the peak occurring around 1843. During this event, Eta Carinae brightened enormously. At its peak, Eta Carinae blazed so intensely that only Sirius outshone it in the entire sky. Consider what that means. Sirius is only about 8.6 light years away. Eta Carinae is nearly 1,000 times more distant. For a star that far away to rival the apparent brightness of one of our closest stellar neighbors means it was producing an almost incomprehensible amount of light. But the luminosity increase was only part of the story. The critical thing about the Great Eruption is what it ejected. During this event, Eta Carinae expelled somewhere between 10 and 40 solar masses of material into space. Let that number sit in your mind. In a span of roughly 20 years, a single star threw off more mass than 10 of our suns. This material was ejected at speeds of roughly 300 to 600 kilometers per second, forming an expanding cloud of gas and dust that is now known as the Homunculus Nebula. We can still see this nebula today, more than 180 years later, still expanding outward from the star. It is one of the most studied objects in all of astrophysics. The energetics of the Great Eruption are staggering. The total energy released, both as light and as kinetic energy of the ejected material, is estimated at roughly 10 to the 49 to 10 to the 50 ergs. To put that in perspective, this is approaching the energy of a supernova, which typically releases about 10 to the 51 ergs. The Great Eruption of Eta Carinae was within a factor of 10 to 100 of a supernova in terms of total energy. And yet, the star survived. It did not explode. It did not destroy itself. It shed an enormous amount of its outer layers, briefly rivaling the brightness of a stellar death, and then it continued to exist. Diminished? Yes. Changed? Certainly. But alive. This is one of the most remarkable things about giant LBV eruptions. They release supernova-level energies without actually destroying the star. The star expels a huge fraction of its own mass, shines almost as brightly as a dying star, and then settles back down to continue its precarious existence. It is as if the star rehearses its own death, performs a full dress rehearsal of its eventual destruction, and then steps back from the brink. This is exactly the kind of event that earns the name supernova imposter, the term we encountered earlier. The Great Eruption released energy approaching that of a genuine supernova, yet Eta Carinae survived. It emerged diminished, obscured behind the expanding debris of its own making, but fundamentally intact, still burning, still unstable, still capable of erupting again. The exact mechanism that triggers a giant eruption, as opposed to a milder S Doradus oscillation, remains one of the great unsolved problems in massive star physics. The truth is probably some combination of several proposed mechanisms. One leading idea is that giant eruptions are triggered when the star's luminosity exceeds the Eddington limit by a significant margin, not just locally, not just in one small region of the outer layers, but globally, across the entire stellar envelope. This could happen if the star experiences a sudden increase in its nuclear energy production. Perhaps a shell of hydrogen ignites in a flash, or a convective instability brings a burst of energy from deeper layers to the surface. When the luminosity exceeds the Eddington limit across the entire envelope, the radiation force overwhelms gravity everywhere. The outer layers are not just loosely bound, they are unbound. They are being accelerated outward by the star's light with no mechanism to hold them back. The result is a massive, rapid expulsion of material, a giant eruption. This is sometimes called a super Eddington wind, or a continuum-driven eruption. The radiation is so intense that it drives mass off the star's surface continuously, like a fire hose of photons blasting material into space. The mass loss rate during such an event can reach 1/10 of a solar mass per year, or even a full solar mass per year. At those rates, The star can shed 10 solar masses in a decade. This matches what we see in the Great Eruption of Carinae. Another proposed mechanism involves deep-seated instabilities in the star's interior. Stars approaching the end of their nuclear burning lifetimes go through increasingly rapid changes in their cores. Hydrogen fusion gives way to helium fusion, which gives way to carbon fusion, and so on, through increasingly heavy elements. Each transition releases energy in different ways and on different timescales. Some of these transitions can produce sudden bursts of energy deep in the star that propagate outward as waves, reaching the surface and violently disturbing the outer layers. These are sometimes called hydrodynamic eruptions, because they are driven by waves and shocks moving through the stellar interior, rather than by the steady push of radiation from the core. In the case of Eta Carinae, the binary companion may also play a role. Every 5.5 years, when the two stars reach their closest approach, the gravitational interaction between them is intense. The companion star plunges deep into the primary star's extended envelope, stirring up material, transferring energy, and potentially triggering instabilities that wouldn't occur in an isolated star. Some models suggest that the Great Eruption was triggered, at least in part, by interactions with the companion during a particularly close passage. The companion might have grazed the primary star's outer layers, depositing energy and angular momentum, pushing material over the tipping point. The binary interaction deserves a closer look, because the orbital dynamics of the Eta Carinae system are genuinely dramatic. Eta Carinae b, the companion, orbits the primary star in a highly elliptical path, with a period of about 5.5 years. At its farthest point, the companion is roughly 30 astronomical units from the primary, about the distance from our Sun to the planet Neptune. But at its closest approach, called periastron, the companion swoops into within roughly 1.5 to 2 astronomical units. That is comparable to the distance between Mars and our Sun, and at that distance, the companion is plunging directly into the outer reaches of the primary star's enormously extended and loosely bound envelope. During these close passages, the gravitational interaction is intense. Tidal forces distort the primary star's outer layers. The companion's gravity pulls material toward it, creating shock waves where its stellar wind collides with the primary's wind. The energy deposited by this interaction can heat material in the primary's envelope, increasing its temperature and potentially driving it into the opacity ranges where the ion bump amplifies radiation pressure. Some models suggest that periastron passages could act as periodic triggers for enhanced mass loss, possibly even for major eruptions if the conditions in the primary's envelope are already close to critical. The companion acts like a match dropped near fuel that is already heated almost to its ignition point. The lesser eruption of the 1890s provides additional evidence for repeated instability. This event was smaller than the Great Eruption, but still remarkable by any normal standard. During the lesser eruption, Eta Carinae briefly brightened again and ejected additional material, which now forms part of the equatorial structures visible between the two lobes of the homunculus. The lesser eruption occurred roughly 50 years after the Great Eruption, and some astronomers have noted that this timescale is roughly consistent with about 9 orbital periods of the binary system. Whether the orbital dynamics played a direct role in triggering the lesser eruption remains uncertain, but the temporal coincidence is suggestive. What is clear is that Eta Carinae's eruptions are not singular events, but part of an ongoing pattern of violent mass loss that has been repeating for thousands of years. Spectroscopic and imaging studies of the material surrounding the homunculus reveal distinct layers and shells at different distances from the star, each moving at different velocities, each with slightly different chemical compositions, evidence of separate ejection events at different epochs. Each eruption is shaped by the interplay between the primary star's internal instability and the gravitational perturbations introduced by its companion. The binary system does not cause the instability. The primary star is already critically unstable on its own, but the companion's periodic close passages may modulate the timing and severity of eruptions, turning a star that would already be violent into one that erupts with a quasi-periodic rhythm tied to its orbital dynamics. There is also the question of what role the iron opacity bump plays in giant eruptions. We discussed how opacity changes can trigger S Doradus oscillations through a feedback loop. During a giant eruption, this same feedback loop may operate at a much more extreme level. If a disturbance pushes a large amount of material into the critical temperature range where iron opacity peaks, the resulting increase in opacity could trap an enormous amount of radiation. The trapped radiation builds up pressure. The pressure drives the material outward. As the material expands and more of it enters the opacity peak, more radiation is trapped, more pressure builds, and the eruption grows. In this scenario, the iron opacity bump acts as an amplifier, turning a modest disturbance into a catastrophic eruption. It is important to understand that these mechanisms are not mutually exclusive. In reality, giant eruptions probably result from a combination of factors acting together. A star near the Eddington limit, with opacity instabilities in its outer layers, experiencing a surge in energy from internal nuclear processes, possibly perturbed by a binary companion. All of these factors can compound and interact in ways that produce an outcome more violent than any single mechanism would produce alone. The star is already on a knife's edge. It doesn't take much to push it over. Now, let me be precise about what tearing itself apart actually means, because this phrase can be misleading if you picture a star literally ripping in half or exploding into fragments. That is not what happens. When we say an LBV tears itself apart, we mean something more gradual, more iterative, and in some ways more agonizing than a single explosive destruction. The star sheds its outer layers in repeated episodes of violent mass loss. Each eruption strips away some fraction of the star's envelope, its outer hydrogen-rich layers. Between eruptions, the star continues to lose mass through its stellar wind, which is much stronger than the wind of any ordinary star. Over tens of thousands of years, through the combined effect of eruptions and winds, the star loses a significant fraction of its birth mass. A star that was born with 100 solar masses might lose 40 or 50 solar masses during the LBV phase alone. That material doesn't vanish. It forms the expanding nebulae and shells that surround every well-studied LBV. The homunculus nebula around Eta Carinae is the most spectacular example of this process. It is a bipolar structure, shaped roughly like two enormous lobes extending in opposite directions from the star, with a thin equatorial disk between them. The two lobes span roughly 1 light-year from tip to tip. They contain an estimated 10 to 40 solar masses of ejected material, expanding outward at speeds of several hundred kilometers per second. The lobes are dense enough to block much of the star's light. Before the Great Eruption, Eta Carinae was probably visible as a bright, naked-eye star. After the eruption, as the ejected material expanded and cooled, it formed a thick shell of dust that now obscures the central star. Today, Eta Carinae is visible to the naked eye, but only barely. Much of its light is absorbed by the homunculus and re-emitted as infrared radiation. The star is hidden behind the wreckage of its own eruption. The equatorial disk between the two lobes is also significant. It is thin and dense, and it contains material that was probably ejected at a different time or through a different mechanism than the lobes. Some astronomers believe the disk was produced by a separate eruption in the 1890s, a smaller event known as the Lesser Eruption. This suggests that Eta Carinae has experienced multiple eruptions at different times, each depositing a new layer of material around the star. The homunculus is not a single eruption product. It is a composite, built up from multiple violent episodes over decades. The existence of these nested structures is one of the most telling features of LBV behavior. The eruptions are not isolated events. They are recurring. The star erupts, settles down temporarily, and then erupts again. Each eruption strips away another layer. Each layer of ejected material joins the expanding cloud of debris from previous eruptions. Over time, the star builds a complex environment of gas and dust around itself, a testament to its ongoing self-destruction. And between the eruptions, the star's powerful stellar wind continues to erode its surface. LBV winds are much stronger than those of ordinary stars. While the Sun loses mass at a rate of roughly 10 to the negative 14 solar masses per year, a trickle so slow it's essentially negligible over the Sun's lifetime. LBVs lose mass at rates of roughly 10 to the negative 5 to 10 to the negative 4 solar masses per year. That means an LBV can lose the equivalent of the Sun's entire mass in as little as 10,000 to 100,000 years. And during giant eruptions, the rate spikes to 10 to the negative 1 to 1 solar mass per year or more. Combined, the wind and the eruptions can strip away tens of solar masses from the star during the LBV phase. This progressive stripping has profound consequences for the star's future. As the hydrogen-rich outer layers are removed, deeper layers are exposed. Layers that are enriched in helium and heavier elements from nuclear processing in the star's core. The star becomes hotter as these deeper layers are uncovered. Its surface composition changes, showing less hydrogen and more helium and nitrogen. The star is gradually being peeled, layer by layer, like an onion being skinned by the force of its own radiation. This peeling process is not smooth or steady. It is punctuated by eruptions and oscillations, interrupted by periods of relative calm, and complicated by the star's internal evolution. The core continues to burn through successively heavier elements, changing the energy output and internal structure. The envelope responds to these changes in ways that are difficult to predict. Each eruption changes the star's mass, which changes its gravitational pull, which changes the Eddington limit, which changes the conditions for the next eruption. The system evolves, and each stage sets up the conditions for the next. This is what it means for a star to tear itself apart. Not a single dramatic explosion, but a prolonged, violent, iterative process of self-dismantlement. Each eruption takes a piece of the star. Each wind carries away a little more. Over thousands of years, the star is stripped down from a massive, hydrogen-rich blue supergiant to a smaller, hotter, helium-rich object that barely resembles what it once was. The process is messy, chaotic, and spectacular, and it leads inevitably to the next stage of the star's life, a stage where the outer layers are gone, the core is exposed, and the star faces its final, terminal destiny. The eruptions of LBVs also produce something else worth noting. They enrich the surrounding interstellar medium with processed material. The gas that is ejected from the star during eruptions is not pristine hydrogen. It has been partially processed by nuclear reactions inside the star. It contains elevated levels of nitrogen and helium, products of the CNO cycle that operated during the star's main sequence life. When this material is expelled into space, it mixes with the surrounding gas and contributes to the chemical enrichment of the galaxy. Future generations of stars that form from this enriched gas will contain heavier elements, enabling the formation of rocky planets and ultimately the chemistry necessary for life. The violence of LBV eruptions is, in this sense, creative as well as destructive. The star is destroying itself, but it is also seeding the galaxy with the raw materials for future worlds. This dual nature, destruction and creation, violence and enrichment, is one of the most profound themes in all of astrophysics. The most violent processes in the universe are often the most productive. Supernovae destroy stars, but scatter heavy elements across galaxies. LBV eruptions tear stars apart, but enrich the interstellar medium with processed material. Even the act of a star dying can be the beginning of something new. And the most extreme LBVs, the most massive, most luminous, most violently unstable stars, are among the most significant contributors to this cosmic cycle of death and renewal. But before we can talk about renewal, we need to talk about what comes next. Because the LBV phase does not last forever. It cannot. The star is losing mass too rapidly. It is shedding its outer layers too violently. At some point, the hydrogen envelope is gone. The star has been stripped down to its core. And when that happens, it enters a new phase. A final, brief, furious phase that leads to the most violent event in the universe, the death of a massive star. And that is where we go now. We have followed the story of luminous blue variables from their origins in the physics of extreme mass and luminosity, through the mechanisms that make them unstable, through the eruptions that tear their outer layers away in violent, repeated episodes of self-destruction. And now we arrive at the final question. What happens next? What becomes of a star that has spent thousands of years dismantling itself? Where does all of this lead? Because the LBV phase is not the end of the story. It is the climax. And the climax leads inevitably to a conclusion that is even more violent, even more dramatic, and even more consequential than anything the star has done up to this point. Let's start by looking at the wreckage, because the remnants of LBV eruptions are not just scientifically interesting, they are stunningly beautiful, and they carry within them the entire recorded history of a star's violent past. The homunculus nebula around Eta Carinae is the single most spectacular example of what an LBV eruption leaves behind. When you look at images of this structure, you are seeing something extraordinary. Two enormous lobes of gas and dust, each one stretching roughly a third of a light year outward from the central star, expanding at speeds of several hundred kilometers per second. Between the lobes, a thin equatorial disk of denser material forms a skirt around the star's waist. The entire structure spans roughly 2/3 of a light year from tip to tip, created by a single eruption from a single star in a span of roughly 20 years. The material was ejected during the Great Eruption of the 1840s and has been expanding ever since. By comparing images taken years apart, astronomers can see the lobes physically expanding, moving outward. This is not a static relic, it is a living, evolving structure, still carrying the energy and momentum of the eruption that created it more than 180 years ago. All that mass expelled during the Great Eruption, the 10 to 40 solar masses we discussed, is still out there, still expanding. This gas and dust is rich in nitrogen and helium, products of nuclear processing inside the star. The material has cooled significantly since it was ejected. Much of it has formed dust grains, tiny particles of solid material that absorb the star's intense ultraviolet and visible radiation and re-emit it as infrared light. This is why Eta Carinae is one of the brightest infrared sources in the sky. The star itself is still enormously luminous, still producing roughly 5 million times the luminosity of our Sun. But much of that light is intercepted by the homunculus before it can reach us. The dust absorbs it and re-radiates it at longer wavelengths. We see not the star's direct light, but the glow of its own ejected debris, heated by the radiation that created it. But the homunculus is not the only structure around Eta Carinae. Outside the homunculus, there is an older, larger, fainter nebula called the outer ejecta. This structure spans several light years and was probably produced by eruptions that occurred thousands of years before the Great Eruption. The outer ejecta shows that Eta Carinae has been erupting repeatedly over a long period of time. The Great Eruption was not the first, it was merely the most recent and most spectacular in a series of violent episodes stretching back millennia. Each eruption deposited a new layer of material around the star, building up an increasingly complex environment of expanding shells and filaments. This nested structure is a hallmark of LBV behavior, and other LBVs show similar features. The nebula around AG Carinae, expelled in eruptions roughly 10,000 years ago, contains an estimated 15 solar masses of processed stellar material, still expanding outward from the star. P Cygni has expanding shells visible in spectroscopic observations. HD 168625, another LBV in the Milky Way, is surrounded by a detached shell of material that was ejected in a past eruption. In every case, the nebula tells the same story. A star that has been shedding enormous quantities of material through repeated violent outbursts, building up layers of debris around itself like the rings of a tree, each ring marking another eruption, another episode of violent self-destruction. These nebulae are not just beautiful, they are scientifically invaluable. By studying the composition, mass, velocity, and structure of the ejected material, astronomers can reconstruct the history of the star's eruptions. They can determine how much mass was lost, how fast the material was moving, what the material is made of, and when the eruption occurred. This allows them to build a timeline of the star's mass loss history, tracking how it has changed over thousands of years. And this timeline is essential for understanding where the star is headed, because the amount of mass a star has lost determines what it will become when it finally dies. And this brings us to the central question: what happens to an LBV after the eruption subside? Where does the evolutionary path lead? The answer, in the traditional picture of massive star evolution, is this. The LBV phase is a transitional stage. It is a bridge between two other phases of massive stellar life. Before the LBV phase, the star was a blue supergiant, or possibly a main sequence O-type star, hot and luminous but relatively stable, losing mass through moderate stellar winds. After the LBV phase, the star is expected to become a Wolf-Rayet star. The connection between LBVs and Wolf-Rayet stars is one of the most important relationships in massive star evolution. A Wolf-Rayet star is what you get when a massive star has been stripped of its entire outer hydrogen envelope. The hydrogen is gone. What remains is the exposed helium core, intensely hot, intensely luminous, and driving ferocious winds far more powerful and sustained than even the LBV's violent outflows. Wolf-Rayet stars have surface temperatures that can exceed 100,000 degrees. They are among the hottest stars known. Their spectra show broad emission lines of helium, nitrogen, carbon, and oxygen, but very little or no hydrogen. They are, in essence, naked stellar cores, the hearts of massive stars laid bare for the universe to see. The traditional evolutionary sequence for the most massive stars goes something like this. The star begins life as a massive, hot, main sequence star. It burns hydrogen in its core for a few million years. As it evolves and its core contracts, its luminosity increases, and it begins to lose mass through increasingly powerful winds. At some point, it enters the LBV phase, where instability and eruptions dramatically accelerate the mass loss. Over tens of thousands of years, the eruptions and winds strip away the hydrogen envelope. Once the hydrogen is gone, the star transitions to the Wolf-Rayet phase, where it burns helium and heavier elements in its core, while its powerful wind continues to erode what remains. The Wolf-Rayet phase lasts a few 100,000 years at most. And then, the star reaches the end of its fuel, the core collapses, and the star dies in a supernova. This evolutionary pathway from main sequence to LBV to Wolf-Rayet to supernova is the standard picture for the most massive stars. And there is substantial evidence supporting it. The chemical compositions of Wolf-Rayet stars are consistent with being the exposed cores of stars that were once much more massive. The nebulae around LBVs show the progressive stripping of hydrogen-rich material. Computer models of massive star evolution reproduce this sequence when mass loss is included, and the observed numbers of each type of star are roughly consistent with what you'd expect if LBVs are a short-lived transitional phase between blue supergiants and Wolf-Rayet stars. But here is where the story takes an unexpected turn. Because in recent years, astronomers have found evidence that some LBVs may not follow this sequence at all. Some LBVs may skip the Wolf-Rayet phase entirely and explode as supernovae while still in the LBV state, with their hydrogen envelopes still partially intact. This possibility was first raised by a series of extraordinary observations in the 2000s and 2010s. The case of SN 2009 IP is particularly striking. In 2009, a luminous transient was observed in a galaxy about 70 million light-years away. It was classified as a supernova. But here is the strange part. In the years before the explosion, astronomers had observed the same location and identified a luminous, variable star undergoing repeated outbursts. The star's behavior before the explosion was consistent with an LBV. It was showing eruptions and variability characteristic of a star near the Eddington limit. And then it exploded. Not in a minor eruption, not in another imposter event. In what appeared to be a genuine core collapse supernova. This was deeply puzzling because according to the standard picture, LBVs should not explode as supernovae. They should first transition to the Wolf-Rayet phase, lose their hydrogen, and then explode. The presence of hydrogen in the supernova spectrum confirmed that the star had not fully shed its outer layers before dying. It still had a hydrogen envelope. It was still, in some meaningful sense, an LBV when it exploded. Or at the very least, it was a star in a closely related evolutionary state. SN 2009 IP sparked enormous debate. Some astronomers argued it was a genuine supernova preceded by LBV eruptions. Others argued it was an unusually energetic eruption, another imposter, and that the star might still be alive. The debate continued for years, with additional observations gradually supporting the interpretation that the star was truly destroyed. If this interpretation is correct, it means the standard evolutionary pathway is not the only one. Some massive stars can reach the end of their nuclear fuel and undergo core collapse while still in the LBV phase, before they have shed their hydrogen envelopes, before they have transitioned to the Wolf-Rayet state. Other similar cases have strengthened this possibility. SN 2015 BH in a galaxy about 88 million light-years away showed LBV-like outbursts in the decades before a final, terminal explosion. SN 1961V, a historical event in a nearby galaxy, may have been another example of an LBV exploding as a supernova, though the data from that era is limited. And SN 2006 JC showed evidence of a massive eruption just 2 years before a confirmed supernova, suggesting the progenitor star was undergoing LBV-like mass loss immediately before death. These observations have forced astronomers to reconsider the traditional evolutionary picture. The old sequence of main sequence to LBV to Wolf-Rayet to supernova may be correct for some stars, but not all. Some of the most massive stars may evolve so quickly that their cores reach the end of nuclear burning before the LBV eruptions have finished stripping the outer layers. The star runs out of fuel while still partially clothed in hydrogen. And when the core collapses, the resulting supernova interacts violently with the dense shell of material ejected by previous LBV eruptions. The supernova shockwave slams into the circumstellar material at thousands of kilometers per second, producing an extraordinarily bright, long-lasting supernova. These are called Type 2N supernova, where the N stands for narrow emission lines in the spectrum, caused by the supernova shock interacting with dense, slowly moving circumstellar material. Exactly the kind of material an LBV would produce through its eruptions. This connection between LBV eruptions and Type 2N supernovae is one of the most exciting developments in stellar astrophysics in recent years. It suggests that the violent mass loss of LBVs directly shapes the appearance and properties of the supernova that follows. The eruptions that happened decades, centuries, or millennia before the star's death determine what the death looks like. The shells and nebulae created by past eruptions become the medium through which the supernova shock propagates, amplifying its brightness, extending its duration, and producing distinctive spectral signatures. In some cases, the interaction can be so intense that the supernova becomes what is called a superluminous supernova, an explosion far brighter than a typical supernova, visible across enormous distances. Some of the brightest stellar explosions ever recorded may have been powered, at least in part, by the interaction between a supernova shock and the dense circumstellar material shed by LBV eruptions in the centuries before death. The star's own violent history becomes the fuel for an even more violent death. But whether the LBV transitions to a Wolf-Rayet star first, or explodes directly, the end result is the same in broad terms. The core collapses. And what happens during that collapse depends on the mass of the core. If the core mass is below roughly 2 to 3 solar masses, the collapse produces a neutron star, an object about 12 miles across but containing more mass than our Sun, compressed to densities where a teaspoon would weigh about 4 billion tons. The outer layers of the star are blasted outward in the supernova explosion, enriching the surrounding space with heavy elements. If the core mass is above roughly 2 to 3 solar masses, even the nuclear forces holding neutrons together cannot resist the gravitational collapse. The core continues to collapse past the neutron star stage, forming a black hole, a region of space where gravity is so strong that nothing, not even light, can escape. The formation of a black hole from a collapsing massive star is one of the most extreme events in the universe. For the most massive LBVs, those that began their lives with masses above roughly 100 solar masses, the death may be even more dramatic. Some theoretical models predict that these stars could produce hypernovae, explosions far more energetic than ordinary supernovae, possibly accompanied by powerful jets of material and gamma-ray bursts. Gamma-ray bursts are the most energetic explosions in the universe, briefly outshining entire galaxies. If some gamma-ray bursts originate from the deaths of stars that were once LBVs, then these unstable, self-destructing stars are connected to the most powerful events the cosmos has ever produced. The question of what compact remnant an LBV leaves behind is more nuanced than it might first appear. The critical factor is the mass of the core at the moment of collapse, and this depends enormously on how much mass the star shed during its lifetime. A star that was born with 120 solar masses but lost 60 or 70 solar masses through LBV eruptions and Wolf-Rayet winds might leave a core of only 15 to 20 solar masses. A star that retained more of its mass, perhaps because it exploded during the LBV phase before the stripping was complete, might collapse with a much larger core. In general, stellar cores above roughly 2 to 3 solar masses are expected to form black holes rather than neutron stars. Given the extreme birth masses of LBV progenitors, black hole formation is considered the most likely outcome for most of them. These would be stellar mass black holes, typically ranging from about 5 to perhaps 50 solar masses, depending on how much mass was lost before the collapse. Some theorists have suggested that the most massive stars, those born above roughly 130 to 140 solar masses, might die through a different mechanism entirely, a pair instability supernova. In this scenario, the core becomes so hot that gamma-ray photons spontaneously convert into pairs of electrons and positrons. This conversion removes pressure support from the core, causing a sudden contraction that triggers explosive thermonuclear burning. The result is an explosion so powerful that it can completely destroy the star, leaving no remnant at all. No neutron star, no black hole, nothing but an expanding cloud of debris. If any LBVs are massive enough to die this way, their deaths would be the most energetic stellar explosions possible, significantly brighter than ordinary core collapse supernovae. The supernovae that follow LBV phases also have distinctive observational signatures that astronomers can identify in distant galaxies. Type 2N supernovae, the ones produced when the supernova shock collides with dense circumstellar material, are characterized by narrow hydrogen emission lines in their spectra. These narrow lines are produced by the slow-moving circumstellar gas, the material ejected by LBV eruptions years or decades before the explosion, being heated and illuminated by the supernova shock. The brightness of these supernovae can remain elevated for months or even years, far longer than typical supernova, because the ongoing collision between the expanding shock and the dense circumstellar shell continuously converts kinetic energy into light. Some Type 2N supernovae are among the most luminous stellar explosions ever recorded, visible across billions of light years. Every time astronomers detect one of these distinctive supernovae in a distant galaxy, they are witnessing the final chapter of a story that began with an LBV tearing itself apart through eruptions that may have occurred centuries or millennia before the final death. But even after death, the legacy of an LBV persists. The nebulae it created during its eruptions continue to expand, carrying processed material outward into the interstellar medium for thousands of years after the star is gone. The heavy elements synthesized in the star's core and scattered by the supernova mix with surrounding gas clouds, enriching them with carbon, oxygen, silicon, iron, and dozens of other elements. These enriched gas clouds eventually collapse under their own gravity, forming new stars and new planetary systems. The material that was once inside an LBV ends up in the cores of new stars, in the rocks of new planets, in the chemistry of new worlds. Everything around you was built from atoms that were once inside stars. The iron in your blood, the calcium in your bones, the oxygen you're breathing right now, all of it was forged in the cores of massive stars and scattered across the galaxy by supernovae. And some of that material may have passed through an LBV first. It may have been ejected in a violent eruption millions or billions of years ago, expelled from a star that was too luminous to hold itself together, thrown into space by the force of its own light. That material drifted through the galaxy for millions of years, eventually becoming part of the gas cloud that collapsed to form our solar system, our sun, our planet, and ultimately, you. This is the profound connection between the most extreme, most violent, most unstable stars in the universe and the everyday matter that makes up our world. The violence of LBV eruptions and the supernovae that follow them is not just destructive, it is essential. Without the mass loss of massive stars, without the eruptions and explosions that scatter heavy elements across galaxies, rocky planets couldn't form. Complex chemistry couldn't develop. Life as we know it could not exist. The universe needs its most dangerous stars. It needs their violence and their instability because that violence is what seeds the cosmos with the raw materials for everything that comes after. So, what does a luminous blue variable really represent? It represents the absolute extreme of what a star can be. It represents the boundary between stellar existence and stellar self-destruction. It represents a regime of physics where the fundamental forces that govern the universe, gravity and radiation, collide with nearly equal strength, and where that collision produces the most spectacular, most violent, most dramatic behavior any star can exhibit short of its final death. An LBV is a star that shines so brightly that its own light becomes its enemy. A star where radiation, the very energy that pours from its core, pushes against gravity with a force so immense that the star's outer layers are only loosely held. A star where opacity changes in the envelope create feedback loops that amplify small disturbances into catastrophic eruptions. A star that sheds 10 or 20 solar masses of material in a single event, blasting its own flesh into space at hundreds of kilometers per second, briefly rivaling the brightness of a supernova, and then somehow surviving to do it again. An LBV is a star at war with itself, and eventually, inevitably, it loses that war. Either it strips itself down to a Wolf-Rayet star and then explodes, or it explodes while still in the LBV phase, its death shaped by the very material it ejected during its life. Either way, the outcome is the same. The star dies, and in dying, it gives back to the universe everything it took, and more. The heavy elements, the processed gas, the energy, all of it returns to the cosmos, where it will be recycled into new stars, new planets, and perhaps new life. The next time you look up at the night sky, at the familiar patterns of constellations, at the steady, calm-looking points of light, remember that among those stars, hidden in their brightness, there may be one that is right now tearing itself apart. A star so luminous that its own light is its greatest threat. A star so massive that it lives on the edge of self-destruction every moment of its existence. A star that will erupt violently, shed its outer layers, and eventually die in one of the most powerful explosions the universe can produce. You cannot see it happening, not with your naked eyes. The distances are too vast, the process is too slow on human timescales, the details too fine for unaided vision, but it is happening. Right now, somewhere in our galaxy, an LBV is oscillating near its Eddington limit. Its outer layers are shifting and expanding, its opacity is climbing, radiation pressure is building, the balance is tipping, and when it tips far enough, when the radiation force finally exceeds gravity by just enough, the star will erupt again. Material will be blasted into space. A new shell of debris will join the expanding remnants of previous eruptions. And the star will settle back down, diminished, lighter, one step closer to its final death. This is the life of a luminous blue variable. Not the quiet, steady existence of a star like our sun. Not the billions of years of calm, stable hydrogen fusion that most stars enjoy. Instead, a brief, violent, spectacular passage through the most extreme regime of stellar physics. A passage marked by instability, by eruptions, by the progressive destruction of the star's own body. A passage that ends in the most violent death the universe has to offer. And in that violence, in that destruction, there is creation. The elements scattered by LBV eruptions and supernovae become the building blocks of future worlds. The iron in your blood may once have been inside a star like Carinae. The oxygen you breathe may have been expelled in an eruption millions of years ago, flung across the galaxy by a star too bright to hold itself together. Every atom in your body has a history that stretches back billions of years through generations of stars, some of which were the most unstable, most extreme objects the universe has ever produced. That is what a luminous blue variable really is. It is a star on the edge, a star too powerful for its own survival, a star that demonstrates in the most dramatic way possible that in this universe there are limits. Limits to how bright a star can shine, limits to how much mass it can hold, limits to how long it can resist the force of its own brilliance. And when those limits are reached, the star doesn't simply fade or dim or quietly expire. It tears itself apart, violently, spectacularly, magnificently. And in doing so, it gives the universe everything it needs to begin again,